In this video, we are going to start talking about some of the more useful interactions between the magnetic field and currents. We've seen that there are forces involved when the magnetic field interacts with a current. We've seen that magnetic fields arise from currents, but as it turns out, there are other things we can investigate, which are very, very useful. So to start that off, we're going to start talking about the idea of flux. This is that word if you've never heard this before. Loosely speaking, flux can be defined as the amount of stuff passing through a particular area. Instead of writing that very loose definition down, why don't I show you some examples to see what we're talking about. So let me take a pipe, and I'm going to fill this pipe with water. Now, we're obviously not going to be talking about water for most of this course, but the idea is we all can visualize this. This is a pipe where water's flowing through the whole pipe. And in this pipe, I can draw several different areas. Let me show you one possible area. Now, this is just not necessarily something that's physical to the pipe. I'm just drawing a loop, which of course a loop will define a certain area. So here, let's say this is area 1. Why not? And then a little further down, let me just draw a different one. We'll say this is A2, and I hope it's obvious that A2 is different than A1. And a little further down, let me draw a different one. We'll say this is A3. And what I've tried to draw, maybe this is not gonna, maybe it doesn't show, but I've tried to draw that A3 and A1 have the same area, but of course A3 has been tilted. So now, let me draw in some water flowing through, and let's see what happens. So there's some water that goes through, some more water that goes through, some more water that goes through, some more water that goes through. So maybe we see what's happening. In the case of A1, if we talk about the flux of water getting through this area, it's quite a lot. In point of fact, all of the water passes through this area. A2 is different though. Only some of the water passes through this area. So if we're talking about the flux through A1, we have to say that the flux through A1 is greater than the flux through A2. We can also look at A3, and remember what I said was that what I tried to draw, maybe unsuccessfully, was that A3 and A1 are the same size, but A3 is tilted. And I think it's obvious, this water line doesn't get through there. We have to say that the flux through A3 is less than the flux through A1, even though they're supposed to be the same size. The difference is, of course, is that I've tilted it. What always comes to mind when I talk about this is waking up in the morning, since my alarm is on my smartphone. Back in the day, we didn't have smartphone alarms. We had alarm clocks, but now everybody, including me, uses their smartphone. Well, the problem with that is when I wake up, my eyes are adjusted to the dark. It's pretty dark in my room, and then there's my phone yelling at me to wake up, and I want desperately to turn it off. But if I try to look to see where the button is, then the phone is so bright that I have to close my eyes. I can barely see it. So, and I for sure can't scroll through a menu and turn the brightness down. So my solution is always to take my phone and turn it, or maybe tilt it. If you need to see what that looks like, turn the lights off in your room and do it with your phone. You'll find that in this orientation, the light is less bright. The phone's still putting out the same amount of light. It's just that not all of it's getting to your eyes. You've decreased the flux into your eyeballs from the phone. And so orientation matters. Size of the area matters. Orientation matters. And then size of the area matters here, and orientation matters. There's another way I could decrease the flux, of course, and that would be to just turn down the water. So let me draw different water lines, this time in orange, so that you can see what I'm talking about. If I didn't have all this water flowing in the pipe, maybe I just had this much. So the orange is supposed to represent a different situation. And you see what happens, right? The flux through this surface of the orange lines has got to be less than the blue lines because they're just fewer lines. So to change the flux, what can I do? I can change the size of the area, I can change the orientation of the area, or I can change just the amount of stuff flowing through the area. All right, let's make this practical. We're going to talk about the magnetic flux since we're talking about magnetism. The symbol for flux is going to be the Greek letter phi. It's basically the Greek F. Sometimes you will see it capitalized. It kind of looks like a TIE fighter turned on its side. Sometimes you won't see it capitalized. I typically don't. I typically leave off the serifs here just to save time. But they're all different kinds of flux. I should point out there's electrical flux, magnetic flux, gravitational flux. Any stuff that can get through an area, there will be a flux associated with that. So to signify that this is magnetic, I'm going to subscript that with a B. Now, to define it, let's see what we can do here. The flux is going to be defined. We've already seen that it has to be proportional to the size of the area, right? So, and it also has to be proportional to the amount of stuff flowing through it. So in this case, we're not have water, we have the magnetic field. So the amount of stuff is B, and the size of the area will just be given by A. BA. Now, what I've done is I've taken care of the amount of stuff and the size of the area. What I haven't taken care of is the orientation, which I can do by adding a little bit of trigonometry, cosine theta. This bears some talking about, so let me tell you what theta is. Let me down here draw a loop, which of course defines an area. There's an area of this loop. And let me go to the direct center of that and draw a vector such that it is perpendicular to the plane of the loop. We're going to call this the area vector. Its magnitude is the actual area of this loop. Its direction is always perpendicular to the loop. And so if I change the orientation of the loop, then I change the orientation of my vector. My vector has to stay perpendicular to this. Fair enough. Now let a magnetic field pass through this loop. So there's a magnetic field here. Let's say this is my magnetic field B. This angle that I'm talking about is the angle between the A vector and the magnetic field vector. That is theta. So notice what happens if we know how cosine theta works. When that angle is 0, right? That means the entire face of the loop, if this is the loop, if I rotate it this way, that means that the A vector is in line with the B vector. In that case, I've presented the entire face of this to the B field, and all of the B field gets through. That's this situation here. If I rotate it up such that the vector looks like this, what I've done is I've taken the loop and I've turned it like this, if you can see that. So actually none of the magnetic field gets through the loop. It all goes above and below it. Mathematically, this is the situation for cosine theta. Well, theta in that case is equal to 90 degrees, and the cosine of 90 is 0, right? Cosine of 0 is 1. So I can maximize the flux by putting my loop like this. I can minimize the flux by putting my loop like this. In terms of the vector, I maximize the flux by putting my vector like this. Minimize it by putting my vector like that. That is magnetic flux in a nutshell.